Hi, my name is Peter Hickman. I'm an instructor at Delgado Community College in New Orleans. My colleague Ashley DeCoux is operating the camera. Welcome to the cloning by paper experiment. We're also going to be doing a little restriction mapping. So I have two colors of paper here. They can be any color. I'm using green and yellow today. The green will be the vector sequence. The yellow represents insert. I'm going to be cutting strips, two strips of each piece of paper so that we can make two different recombinant molecules. Up above, I'm going to get to that in a second. I have a drawing of a SAL1 restriction enzyme site. I have a couple tools to my right, scissors, tape, ruler, some pens. Alright, I'm going to start by going along the long edge of my green paper, whatever the width of this ruler is. I think it's a 1-inch wide ruler. Just going to mark the edges of my strips. Okay, going to do the same thing with my yellow insert. So most of this paper is going to be cut off and wasted. The strips are the key. I'm going to pretend that the edges of the paper were cut with SAL1. That's that restriction site that we're looking at up here. That's a 6-base cutter. Leaves a 5' overhang. So these edges are my SAL1 restriction sites. And I'm going to pretend that I've got some commercial vector that I've cut with SAL1, and then I've got some foreign DNA that I'm cutting with SAL1, and I'm going to combine those two reagents. Combination of vector and insert. Now these pages are 8.5 by 11 inches. So I'm going to mark the edges here. This is going to be 0 inches. This is going to be 11 inches. 0 inches, 11 inches, all the way to the edge. Here, my yellow insert is going to be 0 inches on the left, and this is 8.5 inches on the right. Okay, I'm going to use a pen. I guess I'll use a blue pen, doesn't really matter. I'm going to call this vector. I'm going to plan ahead a little bit. And in parentheses, I'm going to call this orientation 1. This vector strip will be combined with insert in orientation 2. Okay, my insert fragment, I'm going to label it insert. I've got a different colored pen. And I'm going to call this the coding strand. I have really tiny handwriting. I hope you can see that on the camera. So again, insert coding strand. So what I want you to do is envision.
You might want to hold those up.
Okay. Ashley says hold these up. So far, so good. We have vector and insert. All right. So I want you to sort of pretend you can think of these pieces of paper as two pieces of paper laminated together. The top surface would be the coding strand. The back side would be the non-coding strand. SAL1 leaves a 4 base pair overhang. If my vector, for example, were 4,000 base pairs, 4 base pairs out of 4,000, that's just 0.1%. 1/1000th of this distance would be overhanging the edge. 1/1000th of 11 inches is about 1/4 of a millimeter. I know I'm mixing units, inches and millimeters, but the point is, if I were to do it to scale, this would be a very, very small overhang, but an overhang nevertheless. So The vector, I only need to label one side, one surface, because this is going to be my frame of reference. For the insert, however, I do want to label the back side of this thing. I can see I forgot to put my 0 inches over here. Okay. I'm going to flip it around, and you know what? I kind of wrote this upside down, so I'm just going to change my ways right now. I'm going to call this side 0 inches, and this side 8.5. Okay, over here is 8.5. Okay, one more time. 0 inches on the left, 8.5 inches on the right. Okay, I'm going to flip this over in a different colored pen. This might bleed through. Yeah, it's not going to look so great here. So I'm going to write it off to the side. Insert non-coding. I'm going to leave off the word strand. It's just going to be insert non-coding. And this side, it's going to be right to left. So 8.5 inches. This side is 8.5. 8.5. 0 inches on this side. Okay. I'm going to do one more measurement before I begin cutting my strips, and that's that I'm going to pretend that both vector and insert have a restriction site, Sal 1. So here's a drawing of Sal 1. Maybe I can hold this up for you. Whoop. This is a 6-base cutter with a 4-base overhang. So if it were cut with Sal 1, you get 2 pieces, 5' phosphate on the T, 3' hydroxyl on the G. All right. So what am I going to do? I'm going to pretend now we have a second restriction enzyme, XBA1. Sometimes that's called ZABA1, and I've just made up these numbers. It's going to be 4 inches from the 0 mark of the vector. So I'm going to use my ruler. Go 4.5 inches rather, 4.5, and up 4.5. Alright, so this is going to be an XBA1 or ZABA1 site in the vector. Over here, again, I've made up these numbers the night before. I'm going to pretend my XBA1 site is 3 inches from the 0 end. So I'm making my marks 3 inches in. So these are basically map coordinates. Okay, now I'm ready to cut my strips, and hopefully this won't take too long. So this is a project you could do at home. We're trying to see how long it takes to see if we can fit it in a classroom period, along with all the other stuff that we normally do when we talk about cloning and restriction mapping. Alright, the vector's almost done. So just a reminder, a recombinant DNA molecule, by definition, is a recombination of pieces of DNA. In our case, vector plus insert gives us a recombinant molecule. Sometimes I refer to the insert as a foreign piece of DNA, but almost done, almost ready to do my ligation. Alright, so I've laid out my pieces of DNA. My vector is sort of my reference. Orientation 1, I'm going to have the red side up. The coding strand is up, so the 0 inch mark is near the 11 inch mark. For orientation 2, my vector is my reference. It's going to stay like this. And I'm going to flip it over so that the non-coating strand is up and 8.5 inches is near 11 inches. Tape is going to be my ligase. So when restriction enzyme sites come together, although that base pair overlap may not seem like a lot, complementary base pairing happens and the ligase is able to catalyze the reaction of making a covalent bond and sealing the link, the nick. So here I need my ligase in orientation 2. I'm just doing one site at a time. Yikes. You know, one thing I forgot to do early on, I wanted to let you know that our vector sequence has a promoter near the 11-inch end. So we're going to just put a red arrow in saying there's a promoter on the vector going in that direction. The clone that we ultimately want is an insert, the coding strand being driven by the promoter. So this orientation 1 is what we would like to see, but half our reactions are going to be this orientation 2. So I'm going to just seal the other ends to finish my ligation reaction. So these two Sal1 overhangs would come together. And we have, whoops, a circular molecule. Orientation 1, promoter is driving expression of the coding strand. It's a circular molecule, recombinant, green and yellow together. Okay, here's my other recombinant molecule. Need to tape these together. It's my ligase reaction. In a test tube, both ends would be ligated pretty much at the same time. It really wouldn't be one end first and then the other. So here's my second molecule. We have orientation 2, promoter, but the non-coding strand, which is actually facing the opposite direction, it would not produce a functional protein. So let's pretend that we have candidates, E. coli, say, that have been transformed with these two possible recombinant molecules. We take 10 colonies, we do mini preps on them all. We'd expect half of them, or 5 mini preps, to have an orientation 1 and half to have orientation 2. Now how can we figure out which is which? We can take advantage of our XBA restriction site. We're going to do some restriction mapping. So we're going to use the scissors as if it's a restriction enzyme, the XBA restriction enzyme. And here I have an XBA1 site. So the restriction enzyme would cut, and this is orientation 1 I'm working on first. It would cut the vector. Again, I'm just going to do this one step at a time. Let's say the other candidate recombinant molecule, it cuts the vector. Doing this one at a time so that we can kind of lay them out here and kind of see what's going on. And one thing you can't see what's going on is I forgot to measure on the non-coding strand. My site is 3 inches in. So let's do that now. 1, 2, 3 inches in. Okay. So this is going to line up. The XBA1 site lines up with the flip side. That's where it's cutting, 3 inches from the 0 end. So look, when I put these side by side, you can see that from that XBA1 site to the XBA1 site for orientation 1, that's a shorter distance than the XBA1 site in the vector to the XBA1 site in the insert for orientation 2. So that is the key to restriction mapping, that the sites are asymmetric, they're not located right in the middle of these things, and we can see different restriction patterns, different patterns after we digest with restriction enzyme. So now I'm going to cut with the other XBA1 site with my enzyme. So a circular molecule cut twice gives 2 fragments. This is orientation 2. I'm just going to set aside for a second. This is orientation 1. I'm going to pretend that these 2 fragments were run on a gel. The larger band runs more slowly. So if I loaded my gel with the wells up at the top, the negative pole at the top of the bench, and the samples ran towards the positive pole at the bottom, My larger fragment would run more slowly, and the small fragment would run more quickly. So one of the parts of the exercise is you can actually measure these fragments with a ruler. This looks like 10 inches, and this is 9.5 inches. All right? So they're almost the same size, but one band is smaller than the other. On a gel, they'd look like that. How about orientation 2? This is the large fragment. This is the small fragment. Again, you can measure them with your ruler. This is 12 inches, and this is 7.5 inches. So on a same gel, a lane loaded side by side, you get a restriction fragment that doesn't migrate as far as this band, and you get a second fragment for orientation 2 that migrates ahead of this one. So envision your gel. You have two very different patterns. You have almost a doublet here. You have a much wider space there. Both of these fragments are combinations of vector and insert. So I should have pointed that out earlier. Just a reminder, the XBA1 site does not cut at the cloning junction. It doesn't cut in the same place as Sal1. So your fragments on your restriction map are different than the green and yellow fragments that you started with. But you get the idea. You can say, well, say 5 of my candidates have this pattern, 5 of my candidates have this pattern. I want to go back and look at one of the 5 that has this pattern, because I want orientation 1. I want my insert to be expressed by the vector. Okay, that's it. I hope the paper exercise helps you if you do it yourself. Enjoy. Molecular biology on paper.